All right, welcome back. So this time we want to look at the Taylor polynomial for e to the x of degree 6, once again centered at 0. So for all of the e's, the derivative of e is just itself. And so evaluate that at 0, and that's just going to be e to the 0, which is 1. So our e coefficients for every one of these are going to be the same. Okay. And so this would again be the P6 would be the sum as k goes from 0 to 6 of the kth derivative evaluated at 0 all over k factorial x to the k. Because again, we're centered around 0. So working that out, P6 would be plug in 0. Every time we plug in 0, it's going to be 1, right? So that's going to be 1 over 0 factorial would just be 1. Plus 1 over 1 factorial would be 1. Plus 1 over 2 factorial would be 1/2 x squared. Plus 1 over 3 factorial, x cubed, plus 1 over 4 factorial, x to the 4th, plus 1 over 5 factorial, x to the 5th, plus 1 over 6 factorial, x to the 6th. Okay. So that is P6 of x. Pretty easy to do it on e to the x. E to the x is pretty straightforward. Let's just look and see how the approximation works. So e to the x is our function, and then let's put in our P6 polynomial. So 1 plus x plus 1/2 x squared. Oh, there should have been x there. Plus 1 over 6 x cubed. Plus 1 over 24 x to the 4th. Plus 1 over 120 x to the 5th. Oops. Plus 1 over 720 x to the 6th power. And so how good is this? Well, let's zoom out some and actually see that this is okay until we get to around a little bit past 2. A little bit past 2, then these guys start to disagree. And a little bit past 2 the other way as well. They start to disagree. Polynomial does its growth stuff, which e to the x, of course, does not do. So there's what we're dealing with there. So this is pretty accurate up to around about 2.5, where I'm starting to see a little bit of red on the graph. So that's my approximation there. Okay. So it's pretty decent, and that's an easy one to compute.